the flow. The stroke is towards the I element, so I is receiving effort, but that means it is giving the information of flow to the system. And this flow has to be written on the left hand side, on the right hand side, you have to write it in terms of states and parameters. They may be linear, non-linear, it doesn't matter. You have to write this variable in terms of states and parameters. So here you have the state P1, which is the momentum, divided by mass. And I think we are all familiar with this. So it's a simple equation for the flow. And then next is, what does this C element provide to this? It gives effort of flow. Look at the causal stroke. It gives effort. And this is effort 2. So effort 2 is K into Q2. And this is based on the constitutive equation which you have fed into. If it's a nonlinear spring, you can specify the nonlinearity over here. Then we have this damper. What does this damper give to this system? Effort. And this effort can be written as, if it is a linear viscous damper as we have taken here in this case, you can write it as R into flow 3. R into flow 3. Okay. Flow 3. Flow 3 comes from where? In this one junction, all the bonds have the same flow. And the information of flow is coming from only one bond. Which is it? Bond 1. And what is that flow? We have already answered it in the in this question here. We know that this flow is equal to P1 upon M. And so R into flow 1, R into flow 3 is the same as R into flow 1 is the same as R into P1 upon M. Okay. Next is, we ask input related questions. What are inputs to the elements, but not to all elements? We are interested only in those elements which have the capability to remember the history of the system, the state, which are going to contribute state variables to the system. Okay. And we know that we have only 2 of them. So we have only 2 of these variables which are contributing states. It's making a lot of noise. आवाज बहुत आ रहा है. आवाज है. So you can see that what does the system give to the elements with integral causality? It is only the elements with integral causality which will contribute states to the system. And here we have only I and C elements contributing states to the system. So here we will have only C and I element providing states. So we will have a generalized displacement variable and a generalized momentum variable as the states. So we have here, it says that, let's look at the first one. So in the first one we can see that the system gives to this element effort. Okay, this integrally causal element is receiving effort, and this effort, it can be written as effort 4 minus effort 3 minus effort 2. If you look at the algebra for this junction, so effort 1 is equal to effort 4 minus effort 2 minus effort 3, and effort 4 has already been worked out here. Effort 2 has already been worked out in the previous question here, and effort 3 has also been worked out in the previous question here. So you have got all the terms on the right hand side worked out, and you can write them here in terms of states and parameters. So this is your first equation, first system equation. The second equation is obtained likewise. You ask for this element which is having integral causality, what does the system give to it? And you can see that it gives flow 2. And what is flow 2? Who brings in this information of flow into this system if you trace the causal path? This flow 2 comes from comes into this junction only from one bond. It is bond 1. So it is the same as flow 1. Flow 2 is the same as flow 1. And what is flow 1? It has already been attended to in the first part of your algorithm. So flow 1 is already known to us. So here you can straight away say that flow 1 is equal to P1 upon M. Okay. Now you have got two differential equations of the first order. Two first order differential equations. And on the right hand side you can see that you have states. You have in the first equation you have P1 and here you have Q2. And these are parameters R, M, K, F also could be constructed with the help of parameters, the ones which you provided. It may be A sin omega t, okay, or any parameters which you specify. So here this simple system is of second order. Why do we say it's of second order? Because there are two states. This system can be modeled completely with the help of two states. Okay, the minimum number of variables required to model this system is 2, and it's a second order system. And you can always write a higher order system. Since it is a second order system, you can always write it in terms of a set of first order differential equations. And from bond graph, you get this set of first order differential equations directly. Okay? You can convert this set of first order differential equations to a second order differential equation. But then you will get only one second order differential equation. Okay? We can also arrange them in a matrix form. Of course, this is a very simple system, but those of you who are from the electrical instrumentation specialization or with control background, you will understand that they can be arranged in a matrix state space form. So here you have the derivative of the states on the left hand side, and that becomes equal to, so here you can write P1 and Q2, these are our states. Okay, P1 is the momentum and Q2 is the displacement of this spring, and here you have force and here you have 0. So you can see that P1 dot is equal to minus R upon M into P1 minus K into Q2, which is the same as this one, plus Ft, which is the same as this equation. And here you can write Q2 dot equal to 1 upon M into P1 plus 0 into Q2, which is the same as this equation. Okay. So bond graph provides you equations in the form of first order set of differential equations, and this has significance. If you see, first of all, you can directly integrate these using numerical algorithms. You have the popular Runge-Kutta technique, okay, for simulating differential equations, and that requires that the derivative of the variable should be written on the left hand side, and it should be a first order derivative. So you have the first order derivative on the left hand side, and on the right hand side you have states, etc., states, parameters and so on. Time also could be there explicitly. So this form is called as the first order state space form, and in modern control theory, the state space form, of course this is a linear time invariant form, but in modern control theory you may have You may have nonlinear equations, and there may be time varying parameters. So in general you will be dealing with systems which are time varying, which are nonlinear, but you can bring them into a form of first order set of differential equations like this. Let's see whether we can have equivalence with the classical equations. If you take a free body diagram of the same system which we started with, we have the mass here, and here we have the force, and the force due to the spring is K into Q, and the force due to the damper is R into Q dot. And here we have the acceleration of this, okay, we can represent the motion of this. Now if you are to write the equations based on this free body diagram, you can see that we will apply the Newton's law, the Newton's second law, and we will get the rate of change of this momentum of this mass in this direction. It is caused by the resultant of the forces, and the resultant of forces are this F minus this R into Q dot minus K into Q2. So this is the first equation, and you can rearrange it, and you see that you get MQ double dot plus RQ dot plus KQ equal to FT. And this is a single equation but a second order differential equation, and we get this in the classical form. Okay, we are familiar with this, perhaps we have seen this too much in vibration, in a course on vibration, etc. In bond graph, we get our equations in this form. We have the first equation, Q dot is equal to F1 is equal to P1 upon M. This was in fact the second equation, and P1 dot is equal to F minus KQ minus R by M into P1. Now we can substitute P1 from the first equation and put it here, and we get MQ double dot is equal to Ft minus KQ minus R by M. And if you take these terms, the last two terms on the right hand side, if you take them to the left hand side, you get exactly the same differential equation. So it is actually the same differential equation but in a different form. But if you are to numerically integrate this form, you will have to again bring it into a form which can be integrated. So you will have to bring it into a first order set, into a form of first order differential equations if you want to apply the Runge-Kutta technique on it. Okay. So in that sense, for numerical integration, the equations that have been derived using bond graph are very convenient because you can directly use them for integration. So now let us go to a little advanced system, not so advanced but still a second order system, but now it is different from our earlier system. We have this mass, but here we have here you have this end which is actually tracking this profile, and here you have the motion of the mass here as V1, here you have the motion of this end V0, and here we start with the model for this. So here we have one junction representing V1, and we assign the inertia M1 to it. Then we apply also this force. It could be the force of gravity, but all that this is showing that the upward direction is assumed positive. So if you are applying gravity, you can write it as minus m into g. Here you have Ft as the force,